Hello everyone and welcome to Coding Challenge. I'm slightly afraid. It's the MandelBulb. It's something that I've wanted to try for a really long time, but I've never really thought that I could do it. I think today is the day where maybe I'll be able to. It's my hope that we're gonna get to the point where we understand the MandelBulb, able to write the code for the MandelBulb, and then you, the viewing audience, will take it from there and make all sorts of beautiful versions of this amazing, intricate, fantastical fractal pattern in 3D. Now, before I get going, I want to mention two previous videos. One is my MandelBrot coding challenge from 6+ years ago. That is the origin story of the MandelBulb itself, as well as my spherical geometry coding challenge, which looks at how to map Cartesian coordinates in 3D space to the surface of a sphere. And we're going to need that same math when taking this 2D fractal, this 2D MandelBrot set, and stretching it, twisting it, extruding it, pulling it into 3 dimensions. Now, this is not a new idea. The MandelBulb itself, this idea of taking the 2D MandelBrot set and making it 3 dimensions, was first proposed in 1997 by Jules Riesz. But if you've seen the MandelBulb before, and it appears in popular culture, I believe it's in the movie Big Hero 6, maybe I could show a clip of that. The one that you might have seen and the one that I'm going to try to make is the 2009 version developed by Daniel White and Paul Nylander. Before I write the code, let's take a step back and let me try to explain the concepts behind what I'm about to attempt to do here. And the place where I really need to start is the MandelBrot set itself. The MandelBrot set appears as a pattern on a complex plane. Well, a complex plane is a very fancy term for a plane of numbers that has a horizontal axis and a vertical axis. The key difference here is that this complex number, which has both a real component and an imaginary component, involves something known as I. I is the square root of -1. This is often referred to as an imaginary number because, I don't know, the square root of -1. I can't calculate that. That must be part of your imagination. But it's actually something very real in theoretical and practical mathematics. Saying that it doesn't exist is like saying, well, negative numbers don't exist because I can't actually make you -3 apples. So to calculate and visualize the MandelBrot set, the idea is to look at every single complex number on this plane. So if I pick this number, I might have a certain value for A, maybe it's 0.4, and a certain value for B, maybe it's -0.2. 0.4 minus 0.2i. And the idea here is to take this number, plug it into C, start with Z equal to 0. So Z iteration 1 equals 0 plus C. So now this is the new value of Z. So at Z iteration 2, I get what's 0 plus C is C, C squared plus C. And then at iteration 3, I'm going to take this value, C squared plus C, square it, plus C, and so on and so forth. And the idea here is if I apply this math over and over again, the result is going to either go to infinity or stay bounded. It's going to kind of oscillate around a stable value. So I'm examining every single point on this complex plane, running this algorithm, and determining whether it stays bounded or tends to infinity. The set of the points that stay bounded, I always get this confused, but the set of the points that stay bounded is the MandelBrot set. If I color all of those points black and all the other points that are not part of the MandelBrot set white, I will see this fractal pattern. So if this is the MandelBrot set, what is the MandelBulb? The MandelBrot set is inherently a fractal that lives in 2 dimensions. Instead of a complex number, could we use something called a triplex number? After all, a coordinate in 3-dimensional space has 3 components to it, x, y, z. So there's plenty more to this story here that I want to map out some of the math to, but I think this is a good time to just take a little pause and actually set up a processing sketch that will allow us to visualize triplex numbers, or in essence, 3D coordinates in space. For this coding challenge, I'm going to use Processing. It's a creative coding framework. It's built in Java. You can download it at processing.org, and I probably have hundreds of videos that talk about it. But check out the website, check out the Processing Foundation to learn more. The reason why I'm using it is because it has a wonderful 3D rendering engine. That exists in P5 too, but I want to explore this in processing first. Let me say a few quick things about the code I have so far. Size gives me a window size of 600 by 600 pixels. P3D for 3D rendering. Window move is just because I'm obsessive and I want the processing window to be on the other side of my desktop here. That's a new feature. I don't know if that name will stay, but it's working right now. And then I have a draw loop and I'm just drawing a background. The first step I'd like to do is just be able to visualize the voxels of a cube. Because ultimately, I'm going to try to place this MandelBulb inside of a fixed space in 3 dimensions. So I'm going to use a variable to talk about the dimensions of a cube. I'm going to call that dim, short for dimensions. So I'm starting off with a triple nested loop for every I from 0 to 32, and every j from 0 to 32, and every k from 0 to 32. Let's create an x, y, z point in 3-dimensional space. And there you see this cube, all of the voxels, all of these 3D pixels, points in 3-dimensional space, making up a cube. Every single point is spaced out between -100 and 100 along the x, y, and z axis. And something that I can do just to make this a little nicer to examine and look at is add the processing library called PeasyCam. PeasyCam will center the view in the center of the processing window itself, so I no longer need this translate. And then once I run the sketch, I can now use the mouse to sort of look around, zoom in and out of this 3D point cloud. If you're wondering what that 500 is doing, that's kind of like the camera position. How far away am I looking at the points that I'm placing in space? So making that 1500, it's quite a bit further away, but I can scroll to zoom in and rotate and spin around. So how do I make the leap from this value c right here, which is a complex number with a x component and a y component, to a triplex number with an x component, y component, and z component? And the answer lies within something called a spherical coordinate. But before I define a spherical coordinate, let's review a polar coordinate first. So in 2 dimensions, a Cartesian coordinate is an xy coordinate, defining a position according to its placement along the horizontal and vertical axis. And I can describe that same point as a polar coordinate. Its position is indicated as a distance from the origin, r, a radius, and an angle of rotation, theta. We can describe points in 3 dimensions in a similar way using Cartesian and spherical. Cartesian having an x, y, and z axis. And a spherical coordinate being described as an r, just like in polar coordinates, a distance from the center, but then 2 angles of rotation, theta and phi. But why do I need spherical coordinates? After all, for the regular MandelBrot set, I didn't need polar coordinates. I could just take this complex number and square it, no problem. So while there might be a way for me to create a version of the MandelBrot set in 3D without the idea of spherical coordinates, the MandelBulb that I want to make, the one that was developed in 2009, uses the idea of spherical coordinates to take a triplex number and square it or cube it or put it to the 4th power and ultimately to the 8th power. So we have to look at a little bit more math before I put this into the code. Remember, the iterative formula that I'm using for both the MandelBrot set and the MandelBulb is as follows. Z equals z. Now with MandelBrot it's z squared, but a more generic form would be z to the n plus c. And now c is a triplex number. So if z equals 0 to start, we have z, the next z is 0 to the n plus c, which is just c. And then the next z is c to the n plus c. And the next z is c to the n plus c to the n plus c. So looking at this math that I'm doing, I need an answer to the question, how do I calculate x, y, z to the nth power? And this is the innovation from Daniel White and Paul Nylander, a formula for taking a vector v in 3 dimensions, x, y, z, and setting it to the nth power. To do that requires the spherical version of that x, y, z vector. We need the r, we need the theta, we need the phi, if you look at that formula. And wander back to this original proposal, which has exactly the formulas written out here. This is how I calculate r, theta, and phi, and this is how I set x, y, z to the nth power. I think I can start to put this in the code now. I'm gonna have to go back and forth between this page and the code many times. So first change I want to do is, while I was plotting the points, it was useful to map all the voxels out to between -100 and 100. I want to now keep all my numbers between the range of -1 and 1. Then from this x, y, and z coordinate, I need to convert that to spherical coordinates. So r is the square root of x times x, y times y, and z times z. Theta is the arctangent of the square root of x times x, y times y, comma z. And phi is the arctangent y comma x. Now, there's certainly efficiencies that I could do in this code in terms of like I'm squaring numbers and doing the square root multiple times, but I'm just going to pre-compute the whole MandelBulb one time in setup, so I'm not going to worry about that right now. Do I need a loop? No, I need a z. I need a c? Let me look back at that web page. Oh yeah, okay, look at this. I need to get a new x and a new y and a new z. Now, processing is wondering, what is n? So n is the order. It is the power to which I am going to set everything in my formula z equals z to the n plus c. And we can try different numbers to get different patterns, but I want to start with the number 8. What's a little bit unfortunate here is that I want to use the variable z to keep track of z and 0, z1 in a loop. But z is also the component of the vector x, y, z. So I think I need a new variable name for this. What if I make it a vector and call it zz? So it's zz. Zeta. Ooh, people are saying zeta. I love that. Okay, let's call it zeta. New variable name makes me so happy. Now I'm going to do something that I really hate doing. And I really hate that I'm about to do this. But I could do it a different way. No, I'm just going to do it the way I hate. I'm going to say while true. Now, generally speaking, if you're going to say while true, you've got a problem, because that's a loop that's never going to end. The only way to get out of a loop that's looping while true, the hard-coded value true that can never be changed, is to put a break in somewhere. So I need to remember, put that break in there, else I'm going to have an infinite loop and everything's going to crash and we're just going to throw away all this footage and I'm going to be done, never come back to another coding challenge ever again. And just to set myself up for success, I'm going to make a variable called max iterations. I'm going to set that equal to 10. And then I'm going to have iteration equals 0. I'm going to say iteration plus plus. If iteration is greater than max iterations, break. Now this is kind of silly because I could have just said while iteration is less than max iterations, but I don't know. This is the way I'm doing it. We'll clean it up later. This int n equals 8 does not need to be in this loop. I mean, it honestly could just be a global variable, but I'm going to put it up here just so I have all the variables I want to mess with. The order of this stuff is going to be important. So zeta starts at 0. And the very first time, I'm taking zeta squared and then adding c to it. So could I make a vector that holds the spherical coordinate, and that is c? I think that's right. So then in the loop, zeta equals power, I mean, this won't work because zeta is a vector, power zeta to the n plus c, right? This is the idea of what I'm doing. I'm doing this every single time. And the way that I take zeta to the power of n are these formulas. So zeta dot x equals new x plus c dot x. The first thing that happens is I need to get these, this should be in the loop. I think it's really going to help me if I have a function to convert from Cartesian to polar. I kind of hate that I'm using the p vector for this, because I'm putting the r in x, the theta in y, and the phi in z, which is quite confusing, because now when I come to do this, this is actually like c dot x. Oh, okay, I'm going to write my own spherical class. Might be totally unnecessary, but I'm going to do it. Just let me figure this out in my own way, please. I'm sure I'm doing this wrong, but I'll get there eventually. So the function returns a spherical object. It's basically just like an object that holds three values, but I want to be able to name those values, r, theta, and phi. So this is spherical c is the spherical version of x, y, z. Power of c dot r, c dot theta, and then, oh, this was a mistake. I'm getting very close. I can feel it. Oh, can't I just do this? Like, isn't that what these are? I've mixed everything up. Let's go back to the whiteboard. C is x, y, z. So c to the n is defined by what I did, and this gives me in my code new x, new y, new z. Then I add c, the original x, y, z to it, and then I take this, convert it to spherical, and do it again to the nth power. Okay. When I said it over there, it made sense in my head, and now I have to see if I can put that into action here. Won't it work if I just start with this? By the way, why am I getting weird little errors here? The variable r does not exist. Oh, I have to define these variables. I think this is fine because I'm starting with 0. So the spherical coordinate 0, 0, 0 is going to be 0, 0, 0. So I could go through this, then add x, y, z to it, and then get the new spherical coordinate, put it to the power of n, then add x, y, z to it again, et cetera, et cetera. I think this is good. I think I've got it. Sorry to interrupt. I really just had to come from the future to acknowledge the fact that this variable c is really unfortunately named. If you look at the formula for the MandelBulb itself, z equals z to the n plus c, there's a c in there, yeah, but it's not that c. Why did I call it that c? Ah! The actual c, the constant, is the triplex number, x, y, z, that I'm adding iteratively each time through this loop. That spherical coordinate is just the spherical version of zeta. So this maybe is a more accurate way to write it. Not that these variable names are that great either, but it's better than putting a false c there. So the rest of the video is going to continue with the c there, but I hope, in case this was a point of confusion for you, that this helps a little bit. As you were. Let's just run this code. Why not? It's not going to visualize anything, but let's see if I get any errors. All right. And if I were to say, like, if I were to multiply these, I mean, I could just use scale, but this math is going to work for every pixel there. Aha, okay, I think we're getting somewhere. So now I just need to figure out, and am I in setup? No, I'm in draw. So here's the thing. I don't want to calculate the MandelBulb over and over again. So I think what I want to do is take this code and put it in setup. Then what I'm going to do is I'm going to create an array of all the points that are within the MandelBulb set itself. That'll be an array list of p vectors. In other words, if at this point, instead of drawing a point, I just say, add new p vector, and I should do something better than just multiplying each value by 100, but that'll be good enough for right now, right? So right now I'm adding every point. I'm doing the MandelBulb math, but I'm not checking what the outcome is. I'm just doing the MandelBulb math and adding every point into this array list. Then in draw, I should still see that cube. Okay, now all I need to do is determine whether or not I should add the point as part of the MandelBulb set itself. So I'm only going to do that if I make it to max iterations. If I make it to max iterations, that means it is bounded. I haven't gotten past some large value. So I also need to test if I've gotten past some large value. How do I do that? Well, I think the easiest way for me to do that would be to check R. R is like the distance from the center. So if R keeps going like way, way, way out, and way, way out like greater than 16, then break. So now only the points where the radius value hasn't gotten past the number 16 will make their way into the MandelBulb set itself. Oh my God. What is the chance that when I run the code right now, I will see something that looks like the MandelBulb after being in this room for like, I don't know, I've been in this room for 4 hours today. I mean, I was doing a lot of stuff before I even started coding because I was so stressed out. Oh, everybody, say your 3D fractal prayer. I mean, there's no way this is going to work, right? No chance. All right, I'm hitting run. I can't look. Wait a second. Okay, that kind of looks like, I don't know, kind of looks like a MandelBulb-y thing. Let's make the dimension 64. Oh my goodness. Okay, so here's the thing. That's the MandelBulb. That's the MandelBulb. I think that's the MandelBulb. Okay, I think I know what I want to do here, which is that let me just make n equal to 1. Just like that cube thing, right? So why is that not a sphere? Somebody will explain this to me in the comments. I thought that would be a sphere. But it's running really slow. The reason is, well, I need some kind of prop, some kind of device. Hold on. Here is a basketball, a little miniature basketball that really needs some air pumped into it. Oh no, it's fine. I'm gonna make this into the MandelBulb. What I have done, I'm plotting every point along the surface of this MandelBulb basketball, as well as every point on the inside. So I think what I want to look for are the points at which the neighbor is a bounded point or a not bounded point, right? Like if I'm looking at where's the edge between this basketball and the rest of the three-dimensional space. Let me go back to 8. So basically, as I'm looking at, I guess K is the z-axis. So I can do it, I can just consider every point along the z-axis. Right before I do this, Boolean edge. So they're going to be, when I start, like the MandelBulb is in the center. So when I start, they're going to be not bounded. So as soon as I find one that makes it to the end, edge is true. So as long as it's not the edge is true, add it to the set. Let's run this. Yeah, so that's like half the shape. You can kind of see it. Can I go up to 128? So you can see I'm just getting the bottom half of the MandelBulb, because I also need to say, if it is an edge, then I can say edge is false, right? This is like, the edge variable is like a switch. Like first it's off and it finds a point on the MandelBulb, in the MandelBulb. It flips it on and places that point. Now it doesn't flip that switch back off until it finds a part that's not, so it can flip it off and then find the next one. I think this is gonna work. Yeah, that's a Pointcloud MandelBulb. Look at that. That's a Pointcloud MandelBulb. We did it. I mean, it looks nothing like the beauty of the like fully ray traced, rendered, colored, lit MandelBulbs, but by golly, my brain somehow made it from the start of whatever I started today to this, and I'm very, very happy. The other thing I can play with is what value of n am I using? And we can see here in this post that these are the shapes that I would get from the power of 2, power of 3, power of 16. Whoa, let's look at that. N is 16 here. Yeah, take a look at that crazy fractal Death Star. Hi, Dan from the future here. Let's wrap this video up. Dan from the past kept going down a road. There was no train there, or it was off the tracks, and didn't really get anywhere. What I've explored here is the math behind the MandelBulb and rendering it as a point cloud. So there's probably some things that you could try to do even with this. Like, is there some logic by which you could choose different colors for different points of the point cloud? Could you render each point of the point cloud as not just a point, but with a texture or some other kind of shape? Could you save all the points from processing and import them into something? I tried my hand a little bit at this using something called MeshLab, and you can see some of the sort of awkward results I'm showing you here. But the MandelBulb fractal, and fractals in general, have so much detail to them that trying to turn it into a mesh isn't a particular viable solution. The most common technique for rendering the MandelBulb in its full spectacular glory is using an algorithm called ray marching in combination with a signed distance function. This is a technique that allows you to render different kinds of shapes in 3D, like a sphere or a cube, but you can also use it to render any kind of shape, or you can estimate the distance to that shape from the eye or camera that's looking at that shape. But if you want to get started on learning about these algorithms, take a look at the website and YouTube channel from Inigo Quiles. It is a literal treasure trove of graphics tutorials and knowledge. Wow. So I don't want this to be the end. I think I'm going to have to just completely learn how shaders work now, learn about sine distance functions, and return someday. I don't know, in 10 years when you're still watching this video and I haven't done it yet, please let me know in the comments. I'm going to return someday to revisit different techniques for rendering the MandelBulb in real time, maybe using shaders, maybe using sine distance functions, maybe just using the point cloud in a different way. I don't know yet. If you are able to make your own creative twist off this Pointcloud MandelBulb, please let me know. Share it with me in the comments, social media, on the Coding Train website, all of the ways. I love you all. I love you for having made it somehow to the end of this video. I can't believe you did. If you did, and thank you. I'll see you soon in the next coding challenge on the Coding Train.